Right. Hi everyone. I am Maximiliano Pozos, and I'm going to talk about the bungee jumping. My team is this beautiful team, and yeah, I'm going to talk about the well. First of all, what is the bungee jumping? Bungee jumping has been popular since the late 1970s, and it basically consists on jumping from a really high platform with a rope tied to your feet. I thought it was on the back, but no, it's on your feet. At first sight, it looks simple, but if you jump, the rope stretches and then it bounces you back. If it's not well made, then you can get hurt, get hurt pretty bad, and that's how we get the funny reels of Instagram of people getting hurt. Oh, sorry. So, what is the bungee jumping? In more detail, it is an activity where the jump is connected to an elastic rope. Um, one end is tied to the jumper's feet, and the other end is fixed to the platform. When you jump, you first free fall, and once the rope reaches its natural length, it starts to stretch. Then stretch is what stop. This stretch is what stops you from hitting the ground and dying. The rope acts like spring. Sorry, like a long spring. That means it follows Hooke's law, which is that the force of the rope is proportional to how much it stretches. We saw this from high school. And if the rope is too stiff, the stop will be too sudden and dangerous. And if the rope is too weak, it won't stop the person in time. So the design of the ropes is crucial. It needs to be perfect. Because if not, people will always die. Okay, so the phase one, it's at the very beginning. The only force acting on the jumper is gravity, which is F equal to m plus g. We all know this, and the velocity interacts as the person falls, and the motion can be modeled as uniformly accelerated motion. Well, like it could be like this. It could be like I don't know, free fall. Yeah, it's not free fall. And this is where potentially energy at the top is transformed into kinetic energy. Until the rope starts to stretch, the rope doesn't do anything. The equation we can use here are simple. Distance falling equals one half gt, and velocity equals g times t. Uh, right. And the phase two The phase two is reaching the lowest point. Now in the second phase here, right here, things get interesting. Once the rope reaches its natural length, it starts just to stretch. From this point on, there are two forces acting on the jumper: gravity pulling down, still m times g, and the elastic force from the rope, which is F equal to minus kinetic force plus x plus the position. And here k is the lasting constant, and x is, well, the it's not the position. Sorry, is the extra stretch of the rope, like beyond its natural length. Like, yeah, x. So the total force is mg minus k plus x right here. No, yeah, this is where the motion becomes more complex because now it's like a mass spring system. This phase ends up when the jumper reaches the lowest point where the rope's upward force completely balances gravity and the person momentarily stops before bouncing back and die with that. And we have them right here, the proving. Yeah. So the modeling and differential equation modeling part is to describe this mathematically. We can use a differential equation that is defined right here. And Newton's second law says F is equal to mass times acceleration. And if we substitute the forces we just mentioned, we get this thing right here. This equation is represent an harmonic oscillator, which is the same principle used to describe springs, vibrations, and even musical instruments. The solution involves sines and cosines, yeah, meaning the jumper's motion is oscillatory. That's why the person doesn't just stop at the bottom. They bounce back up and down until the energy is dissipated, totally dissipated. This is fascinating because something that looks like just a fun theory ride it's actually sorry, a real life application of a differential equation. What you told us in the course that um this will work. I mean, this will be important for us for our lives. Type shit. So to conclude, bungee jumping is not just an adrenaline sport. I mean, it is, but it's not only that. It's a perfect example of physics applied to real life. If the person that designed that doesn't know physics, the person who is jumping is cooked. Oh, sorry. We saw how the gravity and elasticity interact, how Hooke's law guarantee the rope can absorb energy safely, and how the differential equation can predict the jumper's motion. What I personally take from this is that science is literally what makes bungee jumping possible and safe. It's a great reminder that behind extreme sport, there's always math and physics working silently in the background to protect us. Yeah. So thank you for everything, teacher. Thanks for the course. Sorry about this. I haven't slept because it's week 5. And yeah, thank you, teacher. Much love for you, and I will miss you.